Okay? Hello? Hello? Okay, you can hear me now. Sure.
Hello everyone, welcome back to the second talk of the session. We have Ian Petrow from the University College London, and he will talk about Weyl-strength subconvexity for Dirichlet L-functions.
Okay. So thank you very much for having me here. So I'm going to try to sort of give a talk for a general audience. So I'll start with the basics. Okay, there. So the talk is about L functions and upper bounds for L functions. So to me, the kind of prototypical example of all L functions is the Riemann zeta function. So I'll just start with talking about kind of an introduction about bounds for the Riemann zeta function. So what is the zeta function? So it's a function on complex plane. So if you have the point, so if I have a complex number out here and real part of S bigger than 1, it's defined by this absolutely convergent Dirichlet series or Euler product. And so from the point of view of analysis for like analytic questions about the zeta function, we more or less understand the zeta function completely in this half plane. And its salient features are that it's given by the sort of formula in a right half plane. It has got an analytic continuation to the whole plane except for a simple pole at s equals 1. And we understand that pole completely. And it has a functional equation relating s to 1 minus s. So that's going to just rotate the plane 180 degrees about the point s is equal to 1/2. So this area over here, we'll sort of know everything we want to know analytically about this area by referring back to the right half plane. It has polynomial growth in vertical strips, and it has this critical strip, which is where everything interesting about the zeta function happens, analytically speaking. So in this domain, it's more mysterious. And also this is where sort of like a lot of arithmetic information is hidden also. So for instance, the original motivation for studying the zeta function was to prove the prime number theorem, which is this statement about prime numbers. And that's roughly equivalent to the fact that the zeta function does not vanish just on the line at the edge of the critical strip, right over here. So the most interesting place to study the zeta function is on the line of symmetry of the functional equation. So the line going through 1/2, and that's called the critical line. And of course, you all know the statement of Riemann hypothesis. So this talk is going to be about the analytic problem of giving upper bounds on the Riemann zeta function, and specifically on the critical line, where the problem is the most difficult and kind of determines the size of the zeta function everywhere else in the plane. So the first result in this direction goes back 100 years to Hardy, Weyl, and Hardy and Littlewood. So Hardy and Littlewood really kind of applied a method introduced by Weyl, developed by Weyl, to bound the zeta function. And they bounded the zeta function to be bounded by t to the power 1/6. And this significantly improved on an earlier bound of Lindelof that got t to the 1/4 for the zeta function on the critical line. So this exponent of 1/4 is called the convexity exponent. Because basically Lindelof's argument is just, well, I know exactly how big the zeta function is on this line, up to powers of t. It's basically bounded on that line up to powers of t. And so by the functional equation, I know exactly what it is on this line, and then I can just use some version of the maximum modulus principle in complex analysis to interpolate across the critical strip between those two bounds. And okay, it's not literally the maximum modulus principle because it's not a bounded domain, but more or less there's some version of this called the Fragment-Lindelof convexity principle, and that would produce this exponent of 1/4. But you'll notice this kind of convexity proof kind of, it doesn't really use anything number theoretic. There's very little that goes into it. It just uses kind of like, it doesn't even use the Euler product for the zeta function. It just uses the functional equation and the Dirichlet series. So there's very little kind of content that goes in, and correspondingly you kind of get anything out of that exponent. So what did Hardy and Littlewood really do? The new input here is really due to Weyl, but Hardy and Littlewood a few years earlier developed what's called their approximate functional equation for the zeta function. And so here's a statement of their approximate functional equation. And this is closely related to this convexity principle. So the proof of this is, so what do you have? You have that the zeta function on the critical line is expressible roughly as two Dirichlet polynomials of length t to the 1/2. So if s is equal to 1/4, this looks like a partial sum of the Dirichlet series that defines the zeta function. And even though the zeta function is not defined by its Dirichlet series, inside this critical strip, that Dirichlet series only converges absolutely out here. Even though it's not defined by the Dirichlet series on this line, nonetheless, we can still, nonetheless, it still can be given by like a partial sum about length t to the 1/2 of its Dirichlet series. And here there's like there's a dual sum with, instead of plus it with a minus it, but it's of the same length. And this number here is, okay, it's something complicated, but the only thing that's maybe important for us right now is this has absolute value. It's a complex number of absolute value 1. Fine. So this is also like a pretty simple fact. It also kind of just uses the Dirichlet series and the functional equation, just like the convexity bound basically just uses the Dirichlet series and the functional equation. So if I just look at both of these sums and I just put the triangle inequality on it and throw away all the oscillation in n to the it, I recover this Lindelof's convexity bound because it's almost the same proof. Okay, so throwing away all possible cancellation in these sums of length n to the 1/2, or sorry, t to the 1/2, just gets you back to that trivial bound. So anything going beyond this so-called convexity bound is roughly equivalent to being able to find non-trivial cancellation in these sums of what's basically n to the it is this thing of absolute value 1 that oscillates around in sums that are of length t to the 1/2. So maybe it's worth noting that the 1/2, you can kind of remove the n to the 1/2 very easily just by doing an integration by parts argument. So really kind of we're interested in sums of characters n to the it. Okay, so going beyond the convexity bound is the same thing as detecting cancellations. Great. Oh, that's the backwards way. Okay, so Sarah mentioned Weyl differencing method in her talk. So here's how you apply the Weyl differencing, the method of Weyl that I mentioned was Weyl differencing, and here's how you, a very quick one slide version of how you apply it to the Riemann zeta function. So like I said, here I can get rid of that n to the 1/2 at basically no cost. And the method is going to go by, I take this sum and I can maybe restrict it to like a dyadic range of where n runs between like, say, square root of t and 2 square root of t, or, well, okay, forget about this constant. So let's say n runs between like t over 100 to the 1/2 and t over 50 to the 1/2 or something. And I'm going to take that range and chop it into many small subintervals. And then for one of these small subintervals, I can write it as the sum as an exponential sum. And for some range of parameters in terms of t, it turns out only the first 2 terms in the Taylor series are really important to bound this sum. I think this is a slight lie. Maybe I should say instead of b minus a, I should say like some other parameter x, and this should be like the max over x running up to b minus a of this, because you do some integration by parts at some point, but okay, this is morally speaking true. And then what do you do with this quadratic exponential sum as you apply? So this is the method of Weyl differencing. You take your quadratic exponential sum and you square it out and you apply a change of variables. So when you square it out, I think the change, let's see, what you do is you do L is equal to m minus n. And then once I square this out, I'm going to get something like alpha times m squared minus n squared, which is going to be, well, let me just erase the alpha. That's not my point. So I think that's going to be L times L plus 2n. And so if I just change variables, I can rewrite this as a linear exponential sum on the inside with a kind of quadratic exponential sum on the outside. So now the point is that the degree has dropped from 2 down to 1. And then this one, I can just estimate that because it's a geometric series. So I know exactly what the size of this one, and that's a geometric series, and I can put in triangle inequality and throw away this oscillation, and the result is you get something like this. Let me just like draw this function as a function of alpha. So that function looks something like this is 1, and this is 2, and this is 3. It goes up to height. There's mu, and goes out for a tiny ways, and then goes down and goes back up, and then it's periodic. And it only goes down to about 1. So then I think one of the key ideas here is once I have like a sum over many sums. I have like say a sum from like what am I going to do? Like n is equal to like let's say n is about size, so n's on a dyadic range about size square root of t. So n equals to 2t to the 1/2 t to the 1/2. So I'll just write this as many sums. So let's say we just let a is t to the 1/2. So that's a at the bottom end. And so here this is like, so we'll let mu is going to be my increment. And I'll say it's like size t to the 1/6. And so this goes like a plus 1 up to like a plus mu plus dot dot dot. The second one, so it's like n goes. The next one starts at a plus mu plus 1, goes up to a plus 2 mu, and then I keep going until eventually I get to something like n goes from a plus n is like the number of subsums to 2t to the 1/2. So each of these things is like, let's call the typical one sigma I, and you get, so this whole thing is equal to sigma 1 plus up to n plus 1. So the idea is you apply, okay, this is all of this exponential sum. I'll just write it like that. So you can apply Cauchy-Schwarz to this. And so what you're going to get is you're going to have like the sum over I equals 1 to n plus 1 of the sigma I, and then absolute value squared is bounded by a sum of 1, n plus 1, I equals 1. And then this like mu plus min mu 1 over absolute value of sine thing. Okay, I equals 1 to plus 1. Oh, there's a sum in here over L's. Okay, so but the point here is that this thing here as a function of alpha, where alpha is going to be something like t over a plus I mu squared. This is going to be like roughly approximately constant as I vary alpha like this. So I'm going to have like an awful lot of points that are close to the bottom, or at least kind of bounded in a constant range near the bottom of this. And so this Cauchy-Schwarz doesn't lose very much because I kind of have like the constant equal to one vector and another vector roughly pointing in the same direction. So it turns out to be an efficient move to apply Cauchy-Schwarz, and then you just do a lot of bookkeeping and you end up deriving that t to the 1/6 bound. So that's the Weyl differencing method, and there's kind of like fact that there's some sort of like translation invariance of this function. If you like do a small shift, the difference between like the function and the small shift doesn't change by all that much. In here. Well, yeah, we are losing because I'm losing. I'm putting in absolute values and throwing away this. Yeah, it's a piece of zeta function. Okay. No, this is optimal for this method. Okay, so okay, well, I don't know. Maybe never say never. I don't know what that means exactly, but you are throwing something away because you're going to throw away this cancellation here, which is about size mu, which is about size 1/6. So you're going to get a t to the 1/6. But the only point I want to make is there's some sort of like translation invariance of R that you're using. You're using like a property of the Archimedean, of the real numbers here, which is like the translation invariance of this function. Okay, so that's my very quick version of Weyl subconvexity for the Riemann zeta function. So in general, okay, so this is the Weyl bound due to Weyl and Hardy-Littlewood is the first example of a subconvex bound for L-functions, and in general, this problem that I study is one of the problems I study is something called the subconvexity problem, which is the problem of generally estimating L-functions at the center of their critical strips and obtaining non-trivial upper bounds for those. Okay, so what is an L-function in general? So these kind of come up ubiquitously across number theory. So it's a holomorphic function on the plane that roughly has the same properties of the Riemann zeta function that I listed on the first slide. Okay, so the zeta function already is, okay, those properties, if you understood the very top part of the first slide, this is all just kind of a generalization of that. So you have some list of coefficients, and it's a holomorphic function formed by a Dirichlet series in a right half plane, which emits some sort of Euler product expansion. Okay, so that means that these must have some sort of have a multiplicative property to them. And it comes with an integer. So this integer is just 1 in the case of the zeta function, but it comes with an integer such that the product of linear factors here kind of degenerates, or at least it doesn't degenerate outside of, away from the primes dividing this conductor. Okay, and then there's some Archimedean spectral parameters, which I'll call mu pi I. And you have these list of data such that this L function emits a meromorphic continuation to the whole complex plane. And it has a functional equation. So the functional equation ends up being of this shape for some complex number of absolute value 1, depending on pi, but not s. Okay, well, maybe, okay, no, sorry. Maybe it should depend on s, the way I stated it. That's a typo, sorry. Okay, so where here you need to form what's called the completed L function to really have a genuine functional equation going back and forth. And it's formed by having some factors which are built out of the gamma function. Okay, but kind of for the purpose of this talk, there's an invariant that goes with it, which is kind of the right invariant by which to count L functions or study L functions analytically, which is called the analytic conductor. So it's a product of this non-Archimedean conductor, so this arithmetic conductor pi of q, which shows up in the functional equation right here, and these Archimedean spectral parameters, which are the shifts in the gamma function, which make this functional equation work. Okay, so it's this. I'm going to write down in concrete examples what all this stuff is, but it fits into this general framework. So in general, there's for any L function, like on the previous slide, you have a general approximate functional equation. Again, it's a kind of easy fact. So this, see, I put the s in this time properly, unlike in the previous slide. Here, there's a, so in general, because this is like a very soft thing, there's a convexity bound as soon as you have an L function with the previous properties. So you always get this notion of conductor to the 1/4 is always this easy convexity bound. And so The subconvexity problem in general is to show that there exists some exponent delta such that this L function is bounded by something a bit less than 1/4. Okay, and so we really have some kind of instantiation of the Langlands program would predict that all L functions coming from any source, if it's Galois representations or L functions of varieties or something like that, they should all ultimately come from L functions of automorphic form. So a lot of time in the subject, we usually just work with automorphic L functions as our kind of like starting point. And besides automorphic L functions, like we only know the analytic properties of L functions and the fact that they have a or like an analytic continuation to the whole plane because someone has proved a modularity theorem sort of by the only way we know to prove that L functions have the proper analytic properties are by showing a modularity theorem anyway, so we might as well just assume all of our L functions are automorphic from the get-go. Okay, so this question also has a bunch of applications to number theory. It's not just it would be already good enough if you were just interested in L functions and you want to know how big they were, but it has a lot of applications to number theory. So here's just kind of like a list of kind of the most striking examples, but certainly not an exhaustive list. So usually it has to do, the genre, the flavor of applications that you get out of the subconvexity problem have to do with equidistribution problems in number theory. So usually the convexity bound is useless in proving some equidistribution statement, but as soon as you have a small power saving off the convexity bound, you can prove equidistribution. So a famous example due to Duke is the equidistribution of integral points on ellipsoids. So these are spheres of radii, prime radii, 101, 8011, and 104,851. And the blue points are just all the integer points lying on those spheres, and then they've been scaled back down to be unit size so you can compare them, and you can see you're not getting any like scarring where all the integer points lie on like the equator or something like that. The integer points really cover the entire sphere in the limit. So that's a theorem of Okay, so here's just spelling out the things from the previous slide for the zeta function. You have that this conductor is equal to 1 and the Archimedean parameters are 0. So this analytic conductor is really the 1 plus t that you saw from the first few slides. And here's like the history of subconvexity for zeta function. So I already mentioned the convexity bound and Weyl's bound. I'd like to take back these words fine-tuning. Is really like a lot of important, significant ideas that went into improving over this 1/6, but that would be the whole subject of an entirely different talk. So I don't really want to go into it. But mention van der Korput, Weyl, Sierpinski, Huxley, Vinogradov, Bombieri, and Ivanich. But really, the state of the art right now is the result due to Bourgain using his L2 decoupling method, who saves a power of 1/84 off the Weyl bound, which in this kind of universe is like a very large saving off the Weyl bound. Okay, we're still very far away from proving the Riemann hypothesis, or the Lindelof hypothesis, which follows from the Riemann hypothesis, which says that actually you can put a 0 right here. And if you want to know more about exactly what you can prove about the size of the zeta function under the Riemann hypothesis, you can go to Andre's talk next week on Tuesday, who will tell you more about it. Okay, so the next non-trivial set of L functions after the zeta function are Dirichlet L-functions. So a Dirichlet character is going to be a group homomorphism from Z mod QZ cross to the complex numbers, and just you can build a Dirichlet series out of it that has an Euler product. And so these functions are called, the LS chi's are called Dirichlet L-functions. So here there's a non-trivial arithmetic conductor, which is Q. I'm always assuming that chi is so-called primitive mod Q. And all the other data start to be sort of non-trivial. So this one is now, okay, so this has absolute value 1, and it's the value of this quadratic Gauss sum, which is equidistributes around the unit circle, but we can't say more than that. Blah, blah, blah. Okay, so whereas I think, as we mentioned many times in this conference already, where the zeta function counts prime numbers, this one counts primes in arithmetic progressions. So if we just know it's non-vanishing at one single point in the critical shtick, you can already prove infinitely many primes in arithmetic progressions. And then if you know it doesn't vanish on that line, then you get a precise count for them. And maybe I want to draw your attention to this point, which is that the analytic conductor of this Dirichlet L function is now roughly Q times T. So that's kind of our benchmark for the complexity of this L function. In terms, you can understand that in terms of this approximate functional equation, it always takes about the square root of the analytic conductor terms to represent an L function up to a small error term. Okay. Okay, so just linking back to kind of this very general class of L functions that I wrote down. It's actually known that all degree 1 L functions are of this shape. This exhausts the entire class of degree 1 L functions. All right, there we go. Okay, so the convexity bound for a Dirichlet L function is going to be basically Q times T to the 1/4 plus epsilon. And then there was no progress on improving this for a long time until the early 60s when Burgess came along. And so Burgess, let's just work with T is equal to 0. And so if I have L, that would be working on L 1/2 chi, and he proved that it's bounded by Q to the power of 3/16 instead of 1/4. So I just want to emphasize that like the Weyl, this technique due to Weyl for bounding the zeta function totally fails in the Q aspect. I mean, there's no Weyl differencing, and like if you take a Dirichlet character and you look at a small subsum and you shift it a little bit, there's just like no correlation between like neighboring subsums of Dirichlet characters. So this kind of like translation invariance property of the real line is totally absent when I'm looking instead at characters on Z mod QZ. Let's say for Q of prime. There's actually some sort of way you can mimic this in like depth aspect, which would be like Dirichlet characters mod P to the alpha with alpha going to infinity and P fixed. But let's just, I'm mostly interested in alpha equal to 1 and the prime going to infinity. So there's a different argument. You can use Holder's inequality and the Riemann hypothesis for curves over the finite fields to get some sort of bound, but it's not as good as the Weyl bound. So this Burgess exponent represents going like 1/4 of the way between the convexity bound and RH, the RH bound, or the GRH bound. And these kind of exponents 3/16 or 1/6, they kind of represent natural barriers in this problem that come up over and over again in like modern incarnations of these problems. They seem to be kind of natural barriers in the problem that we try to that let us keep our bearings. See how I'm doing. Okay, so so until like 6 years ago, this Weyl exponent was not known in very many situations. We had like the Burgess bound in many situations, but this Weyl bound only in a few situations. So these were only known, as I've already mentioned, for the zeta function. And then also in these sorts of situations where I fix a prime and I take alpha going to infinity. So this is so-called like depth aspect. So there's actually, there's a paper of George Milosevic kind of studying this situation, and then who can actually get a sub-Weyl, kind of go below the Weyl bound for Dirichlet L functions in this depth aspect. And then there's also a paper of Blomer and Milosevic that do like modular forms twisted by a character where the character runs in depth aspect and can recover the Weyl bound in that situation, but they're all kind of like GL1 depth aspect where this would be like non-Archimedean depth aspect at QP, and zeta function is like Archimedean depth aspect. Or they were related to quadratic characters, so like where chi is equal to like the Legendre symbol. So this all kind of starting from the paper of Konry-Ivanic, which I'll talk about in just a second, and then these are all kind of like leading off from Konry-Ivanic's work. Okay, so here's what this paper here, Conry-Ivanich, proved. So we're just going to look at the chi, which have chi squared equal to 1. So since I'm looking at just odd conductors, these are really all coming from quadratic residue symbols. And so they proved that there's some large A such that you can bound this Dirichlet L function by some large power of A times q to the 1/6 plus epsilon. So recovering the Weyl exponent for quadratic Dirichlet L functions. And so they came up with a method, and it used kind of new input from theory of automorphic forms, and also whereas Burgess's bound used Wey's Riemann hypothesis for curves over finite fields, they were able to use the power of Deligne's Riemann hypothesis for varieties over finite fields from really Wey 1 from the 1970s to prove this. Okay, so in more detail now, okay, so this is for, maybe if you don't know what an automorphic form is, here's like an example, and if you do know what an automorphic form is, or you do know what like modular forms are, then these are just basic examples. So here's an example of an automorphic form. So okay, here it should say q greater than or equal to 1, and on a first pass you could just assume q is equal to 1, and assume this Dirichlet character is just the trivial character. Okay, so these examples of automorphic forms are called Moss waveforms, and they're going to be functions on the upper half plane, and then this will just say it's invariant by some group. So if I let q be equal to 1, then this condition here is empty, and you just have SL2Z, the group of 2x2 matrices over the integers with determinant 1. So then this is just saying that, well, this function is invariant by SL2Z, and so this is really a function on the upper half plane mod SL2Z. So you can draw a fundamental domain for that, which looks like this. So this is the upper half plane, and this is a fundamental domain for the action of SL2Z on the upper half plane. So really what you have is you have a function on a shape like this, where these two edges are identified, and then this edge and this edge are identified in some way also. Okay, so you have a function on this sort of, like, as a Riemann surface, it looks sort of like a teardrop with one long, thin point going out to infinity. Hello. Okay. So I'm not just looking at functions, but I'm looking at eigenfunctions of the Laplace operator, and I'm asking for functions that are bounded. Okay, so you have these like bounded wave functions on this Riemann surface, and these are examples of automorphic forms. Okay, so the ones I'm going to be interested in are a little jazzed up. They have, instead of SL2Z, they have this other bigger group, which is going to give this surface many cusps, and it's going to have a genus, a non-trivial genus, so it might have holes and cusps. So I don't know, it looks something like this with maybe like a hole on the inside, something like that. Fine. Okay, so any such thing has a Fourier expansion. And so just based on taking the matrix 1, 1, 0, 1. And the fact that its Fourier coefficients, the dependence on y is exactly of this form, just is a quick calculation involving this differential equation. And so it has a list of Fourier coefficients, and the way we build up the L function is we just put the Fourier coefficients here. Okay, up to some normalization, which I'll brush under. So there's an important fact about these that I need to mention to explain what comes on the next slide. So I'll just write this HITQ psi for the Moss forms on this group, gamma naught of Q, with respect to the character psi that are somehow primitive in a way that they don't come from a smaller group. Okay, so then if I have such a form F for some level dividing Q, then I can form what's called the twisted form. So I can take an F and I can twist it by a Dirichlet character. And I can define that just by taking this Fourier series. So it's not obvious, but if I just multiply the Fourier coefficients by this Dirichlet character, I get something that still respects this transformation property. Which is not obvious, but is true. And I'll call that new modular form f multiplied by chi, f cross chi. And so it's a fact that I'll use that if I take f and I twist it by chi, so I think there's something missing here. I think all these chi should be chi bars. There should be a chi bar here. There should be a chi bar, where bar is just complex conjugate. The result makes the level go from a divisor of q all the way up to q squared on the nose. And it ends up having trivial character here. Okay, so that's just all kind of background to it. Understand Connery and Vonnich's theorem. So what they really prove is they use the method of moments. Okay, so here they're doing a cubic moment. And because chi is quadratic, this modular form is going to be trivial central character, because I guess like 1 times chi squared is 1, so it has trivial character. And it has conductor q squared. So this whole L function, if I think of it as like this L function cubed, if I think of that as like one L function that has conductor like q to the 6th. And here I also have a product of these Dirichlet L functions to the 6th. So I again have like an L function of conductor 6. And they can prove that this is bounded by like q to the 1st. So that kind of makes sense, because if you look at this sum, the number of terms here is about q. So just ignoring the divisor sum and just let m be equal to q, the number of modular forms of level q is linear in q. Okay, and if we believe the Lindelof hypothesis, or if you believe the Riemann hypothesis bound on these are all bounded by the conductor to the epsilon, then this is like a Lindelof on average, or a RH on average bound for this moment of L functions. So f actually is a Moss form in this setup. Yeah, f is a Moss form. Exactly. Yeah, f is a Moss form in this setup. Okay, so then there's a key point, which is that all of these central values of L functions are positive. And that uses, crucially, that this twisted, that should be an f, not a pi. This twisted Moss form has trivial central character. You need that so that this value is even like a real number. And it's posited by some work of Weyl building on earlier work of False-Bourget. Okay, so then what you can do is you can just throw away all the terms except 1 and then take 6th roots and you get Weyl subconvexity. Okay, so here's the theorem that the FSA award was for. So we just realized that you could set up the family a little bit more generally to cover all L functions. Okay, so I think it was for about 20 years, it was just thought that Connery and Vonnich's method only applied to quadratic characters, and we were basically like for some other project, like doing a bunch of calculations with Eisenstein series, and realized that if we just started with modular forms of a non-trivial central character, chi squared, and then twisted by chi bar, you would get trivial central character. So even though f does not have trivial central character, and chi is now not quadratic anymore, this twisted thing still has trivial central character, so that we can apply the positivity arguments. And here it doesn't, again, it's kind of essentially for the same reason, but I have absolute values to even powers, so I get something positive here, or non-negative here as well. Sorry for... So f is a Moss form. This theorem that I'm writing is just for a Moss form. I'm not going to talk about it in this talk, but in the paper, there's also a version where you replace the Moss forms by holomorphic modular forms, and this term is not present. And so we also have the same theorem for holomorphic modular forms, but that's not, you can read the paper for that. I'm not going to talk about that, because I want to focus on the Dirichlet L-functions. So here, b is like some constant. B is actually like 5 plus epsilon. 5 is like a huge constant in this world. So this gives you, okay, and then there's a kind of companion theorem, which is that if t has at least some size in terms of epsilon, instead of looking at like a big window from t goes to the eigenvalues of the Moss forms, or the t in the Dirichlet L-functions go between minus t and t, I look at a short window between t and t plus 1. So then the size of this family has about t terms in it. So this, but I can get a 1 here instead of like a 5 plus epsilon. So really, this theorem here, at the cost of putting in a lower bound on t, is also Lindelof on average for this effectively sixth moment of these L-functions. Okay, so I have this cube-free condition in the paper also. But a year later, okay, so there's some obstruction on cube-free moduli, but then you can remove that. Or, okay, we can bound it and show that it's not so large that it ruins the whole result. That was a follow-up paper. That was not the FSA paper. Okay, let's see. 5 minutes remaining, good. Okay, so this cube-free condition is really, we can remove that also in kind of a follow-up paper. And so the upshot is that now for all primitive chi modulo q, you have this Weyl-strength subconvex bound jointly in T and Q aspects. So recovering, kind of extending finally Weyl's exponent for the zeta function to all Dirichlet L-functions in Q aspect. So in other language, for every degree 1 L-function under the sun, you have this Weyl subconvex bound in terms of the analytic conductor. Okay, so there's just going to be one slide, which is a summary of the proof. So the proof kind of fits into a long tradition in like analytic theory of L-functions, of starting with these L-functions of as these Dirichlet polynomials. So I already talked about the approximate functional equation. We can use the approximate functional equation to expand that sort of L-function. So maybe I should say like this change that we made to change chi to like chi bar with chi not being a quadratic character anymore. The architecture of the proof kind of is roughly the same, but like many of the steps start to go wrong in Connery-von-Itch's proof. So all of these things had to be like generalized a little bit, but we were working on already other generalizations of Connery-von-Itch's results for like the 4 years or something that preceded this result. So we kind of like had all the tools in hand that we had like just developed in some other papers we were working on. So you have to use like, so a tool called the Kuznetsov formula to have some way of averaging those families of Moss forms or families of modular forms. You apply Poisson summation 3 times. So really there's something like kind of GL3 about this lurking in the background, but I won't go into that. Okay, and then there's some, you have to kind of compute the result in a complicated but explicit way. And at the end of the day, after kind of doing all these sort of structural steps, this is what you really get to, and this is the kind of the kernel of the thing. So you have this original cubic moment, and that's related on the other side after doing all these things to a reciprocal dual moment of L functions of this shape. So I'm brushing like, this is just a schematic. I'm brushing a lot of things under the rug. But roughly you have a 4th moment of Dirichlet L functions modulo Q twisted by this complete character sum G chi psi. So here, if I didn't have the G chi psi, I could easily get a Lindelof on average bound for this 4th moment of Dirichlet L functions just by basically using orthogonality of characters and not much more. But with the G chi psi, this thing is much more complicated. Okay, so here's an expression for G chi psi. It's this 2-variable complete character sum involving the psi and the chi that you started with. So if Q is a prime, you have to use Deligne's Riemann hypothesis for varieties over finite fields. But you can show that this has square root cancellation and is bounded by 1 power of Q. And for this, we really need, so this is like, before chi was quadratic in Connery-von-Itch's case, and they had the same character sum, but there's, the way they treat the sum was kind of very special to the chi quadratic case. And we really need to kind of get under the hood of the like Deligne's L-adic cohomology version of the Riemann hypothesis for varieties over finite fields. Like we have to use A2 and kind of do some computations and prove some kind of like L-adic sheaves are irreducible and have the right properties to be able to apply big theorems from Deligne's A2 to prove that this So using kind of the language of trace functions recently developed by Fouvry, Kowalski, and Michel to prove that this thing has the right size. So then you just put in absolute values and you use this algebraic geometry bound, and then that's enough to conclude the Lindelof on average upper bound. So okay, you could in principle go further if you could find cancellation between g chi psi and these L functions. So like in principle, although I think it would be very hard to prove, like these have some signs that probably equidistribute around the unit circle. And so you should have pretty significant non-trivial cancellation here. Okay, so there's a main term that I've suppressed here, since it's just a schematic. But like doing so would be extremely hard because your sums would get extremely long as soon as you opened up this complete character sum. Okay, so I'll just end by saying there's many more recent developments which I didn't talk about because I wanted to kind of focus on the FSA paper. So after we did this, there was some work by Paul Nelson and Balkanova, Ferlenkov, and Han Wu doing generalizations to number fields. So there's I talked about how this like L 1/2 F cross chi bar cubed is really kind of like a degree 6 L function. So you can think of this as like L 1/2 times some Eisenstein series on GL2 times F times chi bar. So this is now a like GL3 cross GL2 cross GL1 L function. So what you could do for a generalization is replace E by a cusp form on GL3, and that's something that's been done by Chonghang Quan. And he introduces like a completely new method to get this period, to get this like Motohashi spectral reciprocity formula too, involving doing period reciprocity along unipotent groups instead of over tori, and using kind of Poincare series in a non-trivial way. So we have some completely new ideas to replace E with a cusp form on GL3. And so there's sort of some forthcoming work with Na Young and Yuka Hugh, who's in the audience also, generalizing this to like supercuspidal representations. And many other things which I'm sure I haven't mentioned. But let me see. Time's it. I'll stop there. I'm 2 minutes. Thanks.
Thank you, Ian, for the wonderful talk. I think we have time for 1 or 2 quick questions from the audience.
Yeah.
The cuspidal GL3, GL2 generalization, what's the kind of result?
So like, what do we have?
Like in which aspect?
So here we've got this 4th power, and so he's going to have something like psi mod q, and then it ends up being in like a 3+1 configuration. So again, kind of ignoring brushing a few things under the rug, it's basically like you have the GL3 cross psi, and then another L 1/2 psi, something like that, times this complete character sum. I can't remember if it's the same complete character sum or a different one, so let me just write G for like some complete character sum. So the GL3 cusp form gets propagated in exactly like this. So in this situation, we don't have. I think it's like okay, so there's no like subconvexity result that I can tease out of this, but this is at least kind of like what the Motohashi formula. So the result is just like we have this Motohashi formula and a new method for getting this Motohashi formula. There's no like subconvexity result that comes out of it.
I see. So it's not even clear that this product of 2 L function is positive, right?
Right.
So here it's automatically positive.
Exactly. That's right.
Okay.
So the GL3 cusp form propagates in this, exactly this way.
Okay, thank you.
Yeah.
Any more questions for the speaker? I think I have a quick question.
Sure.
So in your last line,
yeah,
it's not straightforward from Deline's work that this bound holds. You had to do a lot more work to prove this.
Yeah, it's kind of like there's a machinery, but there's hypotheses to check, and so we have to check some hypotheses, and once you start doing that, you have to start having some L-laddic sheaf and proving that the representation, the Galois representation that goes with it is irreducible, and there's like ways to do that, but we're manipulating, okay, so we have some black box machinery, and we have some basic control of manipulating it to do what we want, but it's basically like checking hypotheses so that we can apply the right theorems to make the thing work. But there's some non-trivial things to check all those hypotheses.
I think we can have the other questions outside. So let's thank Ian again for the wonderful talk.